Hey guys, welcome back to my channel. We have another paper implementation for you today. Today, the paper we're going to be doing is called LoSparse, which is a structured compression of large language models based on low rank and sparse approximation. And this is kind of similar to the Galore paper in that you're compressing the model. However, this is more so for after training as opposed to pre-training or fine-tuning like you see in the Galore. But it's in the same realm of model compression. And this paper is unique because it actually works off some of the prior work of some of these authors, mainly their uh, pruning technique. But this builds off of that and it adds kind of a low rank component to it. Like last time, we're gonna read through the paper, get an idea, and then try to code it from scratch. So this paper, low sparse structured compression, it's a model compression that approximates a weight matrix by the sum of the low rank matrix and a sparse matrix. So they're going to swap out some of the linear layers for a low rank approximation of two matrices, and then adding on to that a sparse matrix. So the idea behind this is that the low rank matrix kind of compresses they call it coherent and expressive parts of the neurons, while the pruning removes the incoherent and non-expressive parts. And the idea is that uh, you kind of get this diversity to expressive neuron trade-off where uh, you kind of keep the diversity and without losing too many expressive neurons is how they put it. In the introduction, they kind of give a little background on pruning methods. So there's two types. They mentioned structured and unstructured. The main difference is how you prune the weight matrices. So if you kind of pretend that you have maybe it's easier if I draw this, but if you have a weight matrix, um, where so if you have a weight matrix, and it's structured pruning would be if you turned everything in this row to be zeros or everything in this column. So it's a column wise or row wise deletion of parameters. Whereas unstructured is like if you took like made this one zero and this one zero and this one zero and this one zero and this one zero. And the difference being that structured is a little easier to do. It's a little less computationally expensive. It's, obviously you just delete the rows or the columns by zeroing them out, whereas unstructured, you have to basically measure every single parameter on their own as opposed to everything in a row and then delete them piece by piece, which can be a little slower. So in this paper, they're going to focus on structured pruning. So their sparse matrix is pruned by structured pruning. They kind of go into some of the caveats of pruning. Obviously, if you have a 100 by 100 matrix and you prune 10% of that, out of the 10,000, you have 9,000 parameters left, right? But the further down you go, the more you prune it. So at a 90% sparsity ratio, you only have 1,000 parameters, and so obviously the model just is kind of suffering brain damage at that point, and it's not quite as good. So they kind of have some graphs of what the weight parameters of a LLM model, BART model look like, the important scores of each parameter. And so you can kind of see it's very kind of bimodal here. There's some that are very important, there's some that aren't very important. Ideally, it's kind of sloped instead of bimodal. But so that's the sparse matrix component. The low rank matrix is similar to the Galore paper. You're computing it by a singular value threshold. So you effectively create a singular value decomposition of the weight matrix, and you keep the you know rank determined by you. So like if you want to keep the top 100 singular values of the weight matrix, you keep that, and that's your low rank component. So this model, as I've said, kind of works on both, or combines both these methods together. So they kind of go into background on what like low rank really means, and give some background on transformer models. So multi-head attention with the self-attention layer of the softmax, and the query key value matrices, not really super important. So in 2.2, they kind of start to dive into how they measure the importance for each parameter or each row, really. So there are certain ways to prune the matrix. One of them is just like a very simple one is magnitude. So obviously, if you have, say, a weight matrix where the range is 0 to 10, all the parameters, you might want to just zero out anything close to 0, because it's already effectively small, and it will compress the model a little bit. So that's one way of doing it. They, however, again, building on their work in, I believe, a prior paper, they work on this method called sensitivity and sensitivity of the uncertainty. So what they do is, while they're training it, they will multiply the weights by the gradient of the loss. So when you're training a model, you call the for loop with the epochs and the optimizer, and you zero out the gradient and do a loss step backward. If you were to somehow stop the model mid loop and you called the weight parameters, each of those parameters would come with a gradient as well, and they are multiplying that weight by the gradient, which is how machine learning works, that you subtract the weights by some learning rate of the gradient. But here you multiply the weights by the gradient, and that's like your magnitude of importance. So the higher that is, the more effect it's going to have on the model, and the more important it is. And because of the way that so obviously this method kind of needs some fine tuning to it, so that you can kind of measure the importance of the parameters. There can be some stochasticity due to sampling. So, if you just kind of have a random data set and you shuffle it, there might be an instance or two where the model updates really shift. And the idea behind this is that they want to kind of account for that. So what they'll do is they kind of smooth it. So in this equation 3 right here, they take like this exponential smoothing average, where they are kind of using this linear combination of this type of parameter b to say that, all right, the importance score is now b times the current importance score plus 1 minus, or b times the previous importance score plus 1 minus b times the new, I guess, sensitivity score of the gradient weight product for the new importance score. And so that smoothing kind of helps deal with, any oscillations you might have in the training data set. And so finally, how do they tie this back to structure pruning? Because at this point, it's very parameter by parameter. So very simply, they just take the mean of the row or the column, whichever way you want to define it, and that's the importance score of, say, a row or a matrix or a column. And so that's how you get the sparse matrix. So the low rank matrix is relatively simple. You have this UV, which, just to kind of review really quick, you compute using, I'm just going to use this one. So UV can approximate like the matrix W. Let's say the matrix W is R1 by R2, and let's just say R1 is equal to R2, and it's both 100. So Again, this matrix is 10,000 parameters, W. So you can make U equal to R1 times, let's call it A, and V equal to R2, or sorry, this would be due to linear algebra, A times R2. And A could be, um, let's just say, uh, 10, 10, a dimension of 10. So when you multiply these two together, they cancel out, and you're left with an R1 by R2 matrix, and it's the same size. But the idea here being that the A is a smaller rank. So, for instance, if A made this U be 100 by 10, yeah, let's just say 10. Uh, if we made U be 100 by 10 and V be 10 by 100, then you have 2,000 parameters, which is a lot less than the 10,000 that was in the original 100 by 100 matrix. And so you just store less. So that's the idea of the low rank matrix projection, where you kind of take a matrix, you convert it into two smaller matrices, and when you multiply those matrices together, you get a matrix. You approximate the original matrix of the original size, but it's less memory to store. So what they're basically doing is they're going through the model, and they are effectively replacing every parameter in there with the low rank projection and the sparse projection. And so that might seem weird to you about how, like, it might seem like you're making the model bigger. And in effect, you kind of are, right? Because to add UV and S, they have to be the same dimensions. And so I've already shown you that when you multiply UV together, you get the parameters of W, which is 100 by 100. So then when you add S into that, S also has to be R1 by R2. So you have this like 2,000 parameter matrix and this 10,000 parameter matrix, right? So you've actually added 2,000 more parameters to store. The cost savings comes from the fact that once you sparsify this 10,000, because it's a sparse matrix, you can, let's just say, make our sparsity ratio 50%. Now we have 5,000 parameters, and now all together it's 7,000 parameters instead of 10,000. And so you've compressed the model slightly, but because of the trade-off between the low rank and the sparsity, it's the idea is that it's a little better than if you just pruned it or you just took a low rank projection. So that's the idea behind that. And so they kind of draw out this little figure showing that W can be approximated by this UV plus S together. So 3.2, they actually come down to the algorithm here. So they show you that the UV singular matrices, UV low rank matrices, are actually calculated by the left singular values and the right. So use the left singular values multiplied by the square root of the top R singular values. So R is something that you choose. You decide to make it 100 or whatever you want. And so the first step is to go through every weight matrix, every linear weight matrix in this model, and initialize the weight parameters as this W minus these low rank projections. So you take weight matrix 0. You can easily create the singular values just by doing a singular value decomposition on the original weight matrix, and then you create S as the difference between the weight matrix and the low rank projection. And so now you've replaced uh, every weight matrix in like a linear or transformer layer with UV plus S. So you basically take one parameter matrix and create three of it. And so now when you're passing it forward, through the forward pass, usually you multiply X, which is your output of the embedding layer, and that's how you do your forward pass. Now your forward pass is going to change, right? Because you have to basically make it multiply by three separate matrices. So so you start off by multiplying X by U, then multiply that product by V, then add the product of X plus S, and that is your new forward pass. And so that's kind of the two-step part to this, where first you have to initialize it, and then you have to rework the forward layer to be able to take these new weight parameters, like how to treat it in the forward pass. And so updating the low rank projections. To update the weight parameters now that you've initialized the all the weight parameters in the model, to now update them, you don't do it at every step because that's wasteful. So similar to the Galore paper, what you do is you kind of pick a iteration to now perform all these updates on. So at the teeth iteration, we now recalculate U and V and S because you just basically take the weight parameter and then just recalculate UV. And then so for S, the sparse matrix, it's very simple where you're just basically updating it as you would a normal weight matrix, where you have the current matrix by the alpha, by the learning rate, and the gradient of the loss. So you just move it along as though it's a regular matrix. Then you again reprune it, but they use this sort of cubic thresholding schedule. And so, you may start with P percentage, and that'll change depending on where in training you are. So, for example, they kind of do these warm up steps and these training steps and the final training steps. And so, for the first few warm up steps, you don't actually prune the matrix at all. Then, as you're in these kind of pre-warm up steps to final warm up steps, you use this cubic thresholding, and then after that, you just use the original P percentage of parameters. So they put this algorithm really nicely for you. It's two steps. You compute the SUD, you initialize, you replace all the matrices, then you compute the gradient. Then as you're training, you compute the gradient for each parameter. And then you update the sparse parameter matrix by basically checking if P depends on where in the training you are, of the parameters are above a certain threshold, and then you basically just update the matrices as you would a normal gradient matrix. So let's try to put this into code. Hey, so we're on to the coding portion, and what I want to do here is to just kind of invoke some simple BERT models, just a simple BERT model, and get like a small data set in, and just kind of show how the model works, because if you read the repo, which it exists, I recommend you do. It helped me write some of my code, especially like the skeleton of it. But what I kind of want to do with this video is just to show you how to implement it in a bare bones fashion. I think a lot of the repo, they kind of make it so that it's easy to do a lot of experiments, but I'm not entirely interested in doing that. I'm just trying to get it to work, basically. So So first thing we need to do is we need to get a data set, agricultural news, and a BERT for sequence classification model. It doesn't really matter what you do. I just kind of wrote my code with the end goal of a BERT model in mind, so it's just a little easier. But we download the data set. I'm only using a very small portion of it, um, just to make it easy to do. Uh, use ChatGPT for this code just because it's very simple boilerplate. We don't really need to go into it. So first things first. So from the LoSparse paper, we need to do two things here. We need to create an SVD, like a low rank factorization, and we need to create a sparse matrix and replace all the weights. So I'm going to bring this page up again. So let's just bring this right here. So what we want to do is, like I said, compute the SVD of the initial of the weight matrix, initialize U and V by 6 and 7, which is the square root of the singular value times the left singular value matrix, and then initialize S0 and then replace all the weights. So let's start with that. So first thing we want to do here is let's just kind of write it out. So we need to do an SVD. We need to do a weight replacement. We need to create the sparse matrix. We need to create the U and V matrices, and then we need to replace everything. So let's start with the SVD. So like what the paper says, we have this function that just calculates an SVD for a matrix with a given rank. So Torch has a really easy library to just do, or a really easy function to just calculate the SVD of the matrix. It'll give you the left singular value matrix, the singular value matrix, and the right singular values. We also want to create this diagonal shape just to make it easy to basically make sure that we're always using the same dimension, the minimum dimension for the rank or the S shape, because sometimes not every so going through like this BERT classification model, some of the matrices we're gonna change are like 3000 by 3000, others are gonna be 768 by 768, and it can be a little bit the dimensions can be a little bit funky. So adding this in helped my code. So we create the left singular value matrix, which so after we get the minimum rank to make these matrices, we create the left and right singular value matrices. This is basically U and V, essentially. So you can see we take the first singular value matrices of the left singular matrix, and then we multiply it element-wise by the square root of the diagonal of the singular value matrix to make it, just exactly the shape that we want. So right here, this is what that code is doing. It's just getting the square root of the singular values times the left and right singular value matrices. So this L and R is U and V. So the next thing we need to do is, and I'm kind of using the way that the code repo wrote this, is to create this new layer, right? So we need to inherit from the PyTorch module class. And let's just kind of get some of the stuff in here. So, so this is how we're going to replace the weight matrices in our model with our U, V, and sparse matrices. So what we need to do here is recreate what we need to put in here. So we need to take the input features number of input features, number of output features, the reduced rank, what level are we going to put this at? And then we also need to check for matrices that have a bias, and we need to make sure that these new matrices will have a sparse matrix as well. So pretty simple, just invoking the definition of the class. And right here, just adding them all to the parameters of the class. So then right here, we are now taking the left and right and making them linear layers, which is going to take the input feature, the reduced rank output feature. And then if we're going to make sparse matrices, add another linear layer. And if we have a bias layer, make it a zeroed parameter, effectively. So this is just, again, helping us substitute the weights in the matrix. So you'll notice that I made this right and left matrix linear layers. That's to make it easier for when we do the forward pass. So I'm going to put that in here right now. So the forward pass. So if you look at the repo, it's very very customizable. It's meant to be for a lot of different models. And again, this is only written for like BERT-based models. So what I've done here is taken it from the repo, but they show you how they're thinking of the forward pass, right? So typically you have our input data x, and it's going to be multiplied by the transpose of the weight plus the bias, if there is one. But now, since we know that the weight is going to be equal to uv, well, let's just use the same function, LR plus s, right? So that's our new weight. So when we multiply x by this new weight, so we're going to replace weight by this, we need to now, just like here, multiply the x by this LR plus s plus b. So this is linear. If you know anything about math, it's there's a distributive property to this, even in linear algebra. So it's the same thing as just taking x times LR times the transpose of L times R plus x times the transpose of s, because obviously we're taking the transpose of this thing. So it's pretty easy. It's pretty simple for what we're going to do. So this LRX is just going to be, we just pass in the right into the left. We just pass the x times the right matrix into the left, and PyTorch makes it very easy to do that. And then same thing with the sparse matrix. We just pass x into our sparse matrix because it's a linear layer, so it's very easy. So our forward pass becomes LRX plus the sparse matrix plus our bias if we have a bias. Otherwise, it's just this plus this. So pretty simple. So that's most of it. We need one more function, and that's to initialize the weights here. So we want to make sure that the parameters that we're working with have a gradient and they're trainable parameters. And we also want to make it customizable for, if we're adding a sparse matrix, which we're always going to be adding a sparse matrix. This doesn't really need to be an if statement, but some of these parameters won't have a bias. So we do need to make it customizable to if there is a bias, just in case when we go through the named modules one by one, we can look and see what the whether there's a bias to it. So this linear LoSparse layer is what's going to replace like an encoder attention query layer or something like that. So let me add the next couple of functions that help us do this. So right here I have this replace weight function. And so what this does is we'll take a model and attribute string, which is basically the name of the layer that we're altering. that layer's matrix, and then the rank that we want to apply to that matrix. So as you can see right here, our left and right matrix is our SVD for the weight matrix we're changing and the rank that we're going to reduce it down to. So it's just calling this function up here. Our S matrix, just like in the paper, how we have we compute our U and V by the SVD, and then we can initialize our S by our weight, our parameter, minus the low rank factorization product of U and V. So same thing right here, matrix minus matrix multiplied of L and R. So, like I was saying before, we're always going to have the sparse matrix, but some of these won't have a bias. So all we have to do is pass in this has attribute function here to the matrix and ask it if it has a bias. Because if it does, it's going to make things easier, right? So what we do here is we create our linear LoSparse matrix, our new weight layer for our replacement, right? So it's going to be the shape of our matrix that it currently is, so we know what to reduce it down to with the rank. It has bias if it has bias, and we're always going to make a sparse matrix for it. So if it has bias, then make the bias matrix what the bias is now. Otherwise, just leave it alone. So then this code down here basically helps us set the attribute for the layer that we want. So if you want to change the layer, what you have to do is just find the module. This is kind of like a recursive function where I'll print out the module names to make it easier, but it basically goes, if you have, say, like it'll come up as like encoder layer 0 attention dot query. Like this attribute parts -1 will be the query, and the parent module will be like the encoder layer 0, and so it just knows to set the query for the encoder layer 0 attention to the linear lower ass instead of the query that we have. So that's for one. So the last thing we need to do is to set it for every matrix. So finally we have this replace weights function. So what this does is we pass in the model, the rank we want, and then the names we want for the matrices that we want to adjust. So right now you don't have to pass anything the way that this is written, and obviously again, we're always going to add sparse. So we're going to be changing anything that has the names query, key, value, dense, or attention in it. So the way that I've done it is we basically have this list of modules to replace. We loop through all the named modules, module names, and then the modules themselves with like the attributes. So this is a string, this is like the actual like linear layer. We check and see if the module's linear. If it's not, then let's skip it. And then if it's also not in any of the allowed names, then let's skip it again. Otherwise, add it to our list of modules to replace. Otherwise, and then so after we've gone through this model and we've gone through and picked out all the linear target layers, we then loop through it again in the modules to replace, and then we replace the weight from up here with our our complete model, our module name, like the layer that we're changing, the actual layer data, and then the rank. And then so we're going to print it out. So this is how you do the first step here of doing initializing all these weights for every weight in the model. So it might be easiest to show what this looks like. So Oh, whoops, because so as you can see, like here's what the current layers look like. So again, we're using a BERT model. So BERT encoder layer 0 attention, BERT layer encoder 0 attention self, and then query key value. So we would be changing these right here, and then this also with a dense layer. And our BERT model is encoder only, so there's no decoder part. But that's effectively what we would be doing. So I could actually run this right now. So we're going to replace the weight. So, like I said, BERT encoder layer 0 attention self query replaced, key replaced, value replaced, dense replaced, the intermediate replaced as well. And we can see that we're actually changing it for every single uh, query key value dense layer in the model. So if I actually click the model and show you, I can show you that it's made of 11 layers, our BERT attention layer, but our BERT attention layer is now composed of our 3 new linear layers. So for example, in the attention layer, we have the query, which has now been replaced by this linear LoSparse, which is the right, the left, and the sparse. So you can see this worked. We've actually changed it, and so seeing that this matrix used to be 768 by 768, but we've changed it into 2 768 by 100 matrices and then a sparse 768 by 768. So that takes care of step number 1 here of initializing the pre-trained weights. So for step number 2, what we need to do is now create the pruner. So I'm going to first copy the construction of it. I'm going to leave that in there for people. So again, keeping in contact with the paper has different ways of doing things. We don't need that. I've shortened it quite a bit just to make it easier to kind of understand what's happening and to see how we go from paper to code. So first things first. So we're going to create this pruner object that we're going to apply every X steps or so to our model, right? Excuse me. And so what we need to know is we're going to need to pass the model in here. We're going to need to pass the mask names, mask parameter names, and non-mask parameter names. The way I've written this code, we really only need the mask parameter name. So because we're only going to be affecting our sparse matrices, right? So we're going to be effectively kind of doing the same thing as we did up here, where we're searching through, all the models, all the modules and module names and modules in the model. So use no mask is false. Threshold is just set to 15%. So 15% is our sparsity ratio. Our final warm up, and max training steps to where we're basically applying that cubic schedule to the pruner and for a maximum number of steps. And then our beta 1 is part of that smoothing between the thresholding, right, from right here. From here. This is our beta right here, because this is what we're going to be using to update the initial pruning importance scores. So first, let's do the thresholding schedule because I think it's probably a little bit easier. So there's 3 ways to go. There's 3 kind of tranches to it, and it's shown right here. back to the so if our current step is less than our initial training steps, don't threshold anything. If our current step is greater than or equal to our initial training step, but it's less than the difference between our max training step and our final warm up step, then we start to use this cubic decay. Otherwise, after we're past that kind of difference tranche, then just apply the 15% threshold. And so it might be easiest to kind of understand what this threshold looks like. So I've noticed something a little bit off about the code. So if you see, again, this is supposed to be kind of a simpler run here. I'm just going to set warm up steps to 10, 25, 50, and then our threshold is going to be 0.5 to start with. I basically create the steps following this logic here, to where we're only going to be doing this line here just to graph it. And we create the threshold plus 1 minus the threshold times 1 minus the cubic nominator divided by the denominator, which is just the, I don't know if you can see it, but it's current step minus initial step minus final warm-up step divided by total warm-up step minus initial minus final warm-up. So same thing down here. So in the code, they have a 1 minus, but it can be a little odd. Right. So I think that changing that from a 1 to a plus kind of makes it a little bit easier to look at. It fits a little bit better, but you do dip below 0. So you could add like a bias here for, these specific parameters. I'm just going to create this 1 minus threshold. It kind of makes it bounce around, but we're always we kind of need the threshold to stay between 0 and 1, because otherwise PyTorch doesn't understand when you try to threshold 10,000% of the values, right? So this isn't following the paper faithfully, but I don't believe that 1 minus this threshold step is correct. So I'm just going to change it because I'm just trying to get something to run here. So we kept that step. So going back to this, so if our step is below our self.warmup step, then we just have this Boolean apply mass to where we're not going to threshold anything. Else, if our step is greater than our warm-up step, but also less than the max training difference, then let's calculate the cubic schedule to degrade this. So I've switched it to a plus, and then I've also had this 1 minus threshold, and we also applied this Boolean apply mask. And finally, if we have our if we're past this step, then just make it whatever we set our initial to. So that's basically what I'm doing here, and also I'm applying a Boolean mask to it. So next step is pretty easy. This is just a helper function to check if, when we're iterating through the model in each layer, if it's part of the mass that we want to, if this is where we want to prune. So we only want to prune the sparse layers, and so this function just helps us make sure that this is the correct parameter to do that. This function will help us basically do a mean row in pruning. So part of this paper mentioned a structured pruning approach, which is where we basically cancel out the rows or columns, right? So in the code that they give you, you have the option to pick like do you want to do row or column, or do you want to do like mean or average, or whatever criteria do you want to set for this? So all this does is just take the mean and just do this across every column. So it'll show us, so it'll basically just create a mean for each row in the matrix, a mean score for the important scores. So next here is this iterative pruning, and I mentioned before that this paper kind of works off of their previous work, which is this like iterative pruning. And this is the part where we kind of get to the calculating the importance score. So this this is what the others have previously worked on, this iterative pruning approach, this exponential smoothing. And so what we're doing here, using this Platon method that they call it in the previous paper. So what we do is for name and parameters in model.name parameters, we check if it's a sparse matrix, and then if we don't have a a key in our like exponential moving average prune scores, then let's just set that to 0 for our I'm using IPT to mean like this gradient score, and then exponential average is like the whole thing. So it's just kind of like an object to kind of store previous versions to make it easy. So if this is the first time we're running this, create a bunch of parameters that are just 0. Then what we want to do is we want to create this self.beta times blah 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 times plus 1 minus self.beta blah 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 blah. So our current score, or our previous score, times like our gradient update. And so down here is where we create the update. So like I said, this IPT score, this importance pruning score, is just the weight matrix, the weight times the gradient of the loss, and it's the absolute value, and we detach it because it's just a number that we don't need to hold. So that's the iterative pruning. So there's 2 more functions that we need to do. So far we have the ability to prune all the parameter scores, or create all the important scores for a model, for a matrix. Then we have the ability to create an average of the score of for each row in the matrix. So now what we need to do is to mask the matrix based off the threshold. So same thing again here. We create this dictionary just to hold our current importance scores, and then we're going to apply our mask to this dictionary, and we're going to get rid of it every time because we don't need to keep it. But so we iterate through our model, our name parameters, make sure that this is a sparse matrix. If the dimensions match up, which they pretty much always will, create a new entry in this dictionary that creates an average score for each for each row in our exponential average importance scores. Okay. Then what we do is we create all the important scores into a easy to read view. So this is just basically just rearranging the data to make it easy for mass threshold. And then mass threshold is this torch.kth value, to where we just make sure that we apply this to all of our thresholds. So we use 0.5, so it's the same thing either way, but so this will give us the indices of all the values that are below our basically our 50th percentile right here. And then so we do our one last importance score. Then we actually fill the mass. So we loop through it again, make sure it's a sparse matrix, and then we take our data and we mass fill to make sure that basically all the indices where our exponential average is below the mask threshold, set it to 0. And then return the mask threshold just to, just to fun, just to see where the cubic scheduling is at. So, that leaves us with one final function here, which is just this, I call it do it all function. So we have the ability to do each thing from the paper that we want to do. So first things first is to create the, it's improperly named, but iterative prune method, which creates the importance scores for all the parameters in the matrix in the model. Then we want to understand where we are in the step process. So we have our thresholding schedule. We're making sure our step is, whether it's in between our final training step and our warm-up step, or if it's time to just apply the final threshold. So, and this will return whether to apply the mask or not. So this will automatically update the threshold and return an apply mask. And so if that apply mask is equal to 1, then we call our mask with threshold on the model for each parameter in the model, and then for each module in the model, and then applying the threshold that we've calculated from the thresholding score. And then I've also added this like mask thresholded function just to see like where it's at. And I kind of already showed you what it's going to look like up here. Maybe it's down here. Yeah, so it's going to bounce around a lot, but that's okay. So I think we've already called the replace weights. Yeah, we did. So now what we want to do is to create the pruner. So you can set these to whatever you want. I'm just kind of making this simple. Forgot to actually define it. And it froze on me. Okay, so let me run that. And now we have our pruner. Okay, so now we finally have our model ready to go. So this is just a simple training function that we got from ChatGPT, where I just basically only added the pruning method right here. Ooh. Yeah, so I don't, you don't really have to do this because it's already kind of like this code up here basically makes this part obsolete, because we're never going to invoke it until the step is actually above it. But what we're going to do here is we're going to run this for like 3 epochs and then create this this step for each step in like the epoch for the enumerator for the train loader, and then we're going to call the thresholding for each step above the initial warm-up steps. So I guess we could just run this. So obviously it's step 10 is when we're going to start the thresholding masks. So you can kind of see it's bouncing around, just kind of like what we thought it would do, or what I sort of showed it would do. This should keep sort of getting, I guess, dip further and further, which it kind of is. And then once it hits step 25, it's just we're just 50 all the way out. So that's pretty much it. I guess I'll let it run and then show you what the results look like. So finally finished training here. Only trained it for about 3 epochs, but as you can see for the training, it just kind of stayed at 50%. Technically, in the paper, the way they do it is that they wait to make sure that the step is a gradient accumulation step. So realistically, I ran this for every step after step 10, which wasn't necessarily needed. But as you can see, loss of about 33%, 44%, 85% accuracy. So it didn't really hurt the model too much, but you know, so down here, I also just kind of created this little uh, investigation into a sparse way just to make sure that it's at 50%. So just taking, a sparse layer of the of a dense layer, and just taking a random row at a random column, I should say, or a random row. Sorry, and just counting how many zeros are in, and then just creating a 50% just as a double check to make sure that after we thresholded the sparse weight matrices that it has is at 50%. So that's the low sparse paper. Hope you enjoyed.